Okay, well, we're going to focus now on the third module for week 4, which is in built-in MATLAB functions. We're going to focus on 3 of these built-in functions. One is a little bit different than the other 2. The first one that is, again, different than the other 2 is called roots. I think it's just worth mentioning here. It's very simple. What it does is find the roots of a polynomial. So, for example, if you have f of x is equal to x minus 3 times x plus 1, we know it has 2 roots then at 3 and minus 1. We do the FOIL method, and what we get is x squared minus 2x minus 3. So all we need to do then to use the roots command is we say c, we give it the array, starting with the highest order coefficient for the polynomial first. So here we have a 1 in front of the x squared, a minus 2 in front of the x, and then a minus 3. So if we simply just say roots c, and we run it, what it'll provide then is an array of of 3 and minus 1. So in other words, we'll get the roots that we expect from that polynomial. So again, very simple, easy to use, and so you'll have it as part of an in-class exercise. But then we'll talk about a couple of other functions that are a little bit more involved, but I think more powerful. The first one is f0. What f0 does is find the root of a function, we'll call it f of x, based on some initial guess, x, it will say the superscript in parentheses 0, so an initial guess. So what does it look like? And I'm going to write it out. It's going to look a little bit ugly, but what will happen is I'll walk you through it and show you how each of these terms works. So it looks like this: x, f val, and a flag, which we'll call it an exit flag, to keep with the nomenclature that MATLAB has. And we call f0. We have at f, x superscript 0, options, and other arguments. Okay, so what are all these things here? So first of all, x itself, let's start with we'll go left to right. X is the root that it's going to solve for. So it'll find the value of x that achieves f of x equaling 0. Fval is the value of f of x at the root, knowing that it won't be exactly 0, it'll be really close to 0, it'll be within the tolerance within the iterative solver that f0 is. So it'll tell you how close you are for that value of x to the actual root, how close you are to 0. Exit flag, there's a number of different exit flags, but what we want is a value of 1. Anything else means that something went wrong. F itself is the function handle. You have to feed it a value of f of x that it's going to be doing the finding the root for. x0 is your initial guess. And options, there's a whole host of solver options that you can use. But I would say that for the vast majority of time, you don't have to do much of anything with the options. The one thing that I do for this class I think is useful is to look at the results from each iteration. So you can just simply have it a line saying options equals optim set. And to do that, you do display iter. So you put that above the f0 call, and what that does then is it sets the options, and as it goes through and does the iterative solve for f0, it'll display the results from each iteration. And then other arguments is a little bit tough. So I'll show you an example here where The idea is that if you have a function that depends on two variables, say x and z, then the other argument would be z. And if you have, obviously if you have additional arguments beyond z, you would just add them into the string, or as arguments into this spot right here. So here we go. I'll show you here how this would work in implementing it in MATLAB. So I'll start a new script, and I'll say function, my function, or something along those lines. So we'll say, actually we'll do a little more robust than that. ME7030, Spring 23, Lecture 4, Example 1. So here's our function. So say we want to find the roots of x squared minus 1. So what is the root of x squared minus 1? And we'll take it to be greater than 0, so we know that the value of x is going to be equal to 1, so that's easy enough. First thing we'll do, though, is because we want to see the values of the iteration of each iteration, we say options equals optimum set, display and iter. So we have that. And we're going to say then that x val exit flag equals f0. We have the function f. We're going to say x0 and options. So we have to give it a value of x0 ahead of time. So we'll give it a value, say, of 2, a starting value of 2, and of course it's going to hopefully converge down to 1. So we have an x0, we have options, we need to give it an f. So down here we have a function y equals f of x. So the value of y will be the value of where we want the value of x squared minus 1 equaling 0. So we'll say x times x minus 1. We end there. And so what we can do then at the end is we can print out all these values then. So x equals %.2e, f val equals %.2e, and exit flag equals %d. So we have x f val exit flag. So if we were to run this, go ahead and save it here. We'll dock it and run it. Let's see that it worked, but I'll show you again. So we'll run it again. So what happens here is that you can see that it tells you for each value of the iteration, which is on the left column here, what's going on. And it has a built-in algorithm that tells you how it's solving for things. But in the end, what it does is it gives you a value of 1 for your value of x, and the value of f val is essentially 0. So it nailed it, which is great. So you have your root of x equaling 1, f val of 0, and exit flag of 1. So everything looks great. Now, what I want to do is show you a couple other things here. As I told you about the other arguments, suppose that we want to provide it a more general function. F is a function of xz, so we'll put a z right there. What we need to do then is we have to put a value of z as an other argument up above. So here we're going to say z equals 1. So we're going to feed it a value of z equals 1. It's going to optimize on x because that's the first argument listed in the string here, and then it's just going to carry z along for the right. So we'll do that here, and it works the same. So it works just fine. Great. Now, there is a second function which I will tell you about for optimization that we'll talk about here. This other function, which is similar to f0, I'll call it a companion to f0, is called fmin bound. What fmin bound does is it minimizes or finds the minimum of a function between 2 points. So it's really a minimization function, not a root solver, but you can use it as a root solver when you simply take the absolute value of the function. So for example, if this is x and this is f of x, and we know our function is something like this. We just take the absolute value of f of x. Of course, it'll follow the curve here, but then it'll bounce up like so. And so the idea is the minimum is going to be right around here. So it'll get you close, but the advantage to it is it's more robust. It doesn't have there's less of a chance of it failing compared to f0. So here you go. It's very similar to f0 again in terms of the nomenclature as well. So x, fval, exit flag. Fmin bound at f. Now, instead of giving it an initial guess, you have to give it a bounds. So you have to give it an x1, which we'll say is right here, and then an x2 right there. So you have to say x1 and x2, or in our case here, to follow the nomenclature of MATLAB, we have an a and a b. So we'll say a and b. So a would be your minimum x, b would be your maximum x for the range you're going to look at. Then you include your other stuff, options, other arguments. So again, A is your minimum x, so we'll say x1, B is your maximum guess, x2. We know options, we know other args, we know the function handle f, and everything else is the same in terms of that. You have the root here, you've got the value at the root is here, and then you have the same exit flag where you want it to be equal to +1 rather. And again, this is a minimization function. So we'll implement that here in just a minute. Just a couple of, again, quick notes so you have it. So here we go. So fmin bound, we'll say, is more stable than f0, but f0 is more precise. So in other words, at the root, f of x closer to 0. All right, so it's more precise than fmin bound. And the way that we implement it is actually very simple. If you have a function f of x, so in our case here we have f and y equals f of x in z, which we used for f0. For fmin bound, we just simply say y equals the absolute value of f of x comma z. And I'll show you how that works here in MATLAB. So here we go. So we'll say this right here is f0. And for fmin bound, we're just going to copy the command over. And instead of an x0, we have to give it an a and a b, so we'll say it's between 0 and 2. So value of 0, value of 2 for that. And we'll copy over this command here. And instead of f0 now it's fmin bound. So we have our values here. Now, instead of f, we're going to call it fabs. So remember, we're taking the absolute value of f. So all we have to do is add another function down here. So y equals the absolute value of f of x and z. So again, we'll clear this off. We'll run this again. Okay, so we'll go ahead and expand that so you can see a little bit better. So here again, we first run f0. Of course, f0 works. You see this right here. We have the value of x equaling 1 and fval of 0, exit flag of 1. That's great. For fmin bound, it's a different procedure. You can see that it gets it close. It gets a root of 1, which is great. We have the right exit flag. But you can see the fl is not quite as precise. It's 2 times 10 to the minus 5, whereas the fval for f0 is within numerical precision is actually 0, which is what we want. So in a nutshell, we have three built-in MATLAB functions you can use. There's roots, which finds the root of a polynomial, very simple to implement. And then you have the two more powerful, more complicated functions. You have f0 and you have fmin_bound. And so I encourage you to explore using these in your work, your research, or other projects and other courses, because I end up using them a lot in my research, especially fmin_bound. I guess my final note is that, yeah, I like to use fmin_bound, but the other thing you could do is you could combine these with your stuff you learned earlier, like say you could use the bisection approach to get you close to the root, and then you can then apply f0 on top of it to then get you to really pin it down to that root and get it very, very precise. So you could consider combining them, and then you have a nice balance between something that's very robust but also very precise.